How's everybody doing? Let me straighten up the camera and we'll get started in about a minute or so. If you look in the description of the video, you'll see the questions. Okay, and we'll try to go through as many questions as we can, maybe stream for about an hour or so. Let me know who's here. Feel free to say hi in the chat. And can you hear? Is the microphone good and all that stuff? Yeah, so let me know in the chat. Flores, welcome. Glad you're here. Let me know if you could hear me or if there's any issues. It's all good. Good. All right, well, it's 5 o'clock, so let's get started. Some of you who joined my live streams back in the early days of the pandemic, back in March and April, know I like to do the simultaneous sip to start all of my live streams and classes. And yeah, so if you'd like to join, now's the time to do so. And it was tradition to type the word sip in the chat if you participated in the simultaneous sip. In class, on Zoom, I can see everybody who does it, but on YouTube, you got to type it in the chat. All right, so I guess the plan is I'll just start with number one, and then we'll work our way through. Black Pen, Red Pen is also doing live calculus. Yeah, I was watching that about an hour ago. He's doing Calc 2. So maybe we'll be able to do that kind of stuff next semester. But for now, we're going to do just a bunch of limits today. And those of you who have taken calculus and are just coming here for a refresher, we don't know L'Hopital's rule yet. Okay, so we're doing limits, old school method. No L'Hopital's, all right? Absolutely no L'Hopital rule today. We're going to have to use conjugates. We're going to have to get common denominators, those sorts of things. All right? So feel free to just mention in the chat if there's a particular question you want to go over. So look at the PDF if there's a particular question. But if not, I'm going to just start with one and I'm going to work my way down. But I'm happy to just go with whatever questions you want. All right, so question one, let me move my water, is so we have this function f of x is equal to x plus the absolute value of x. All right, so we have this function f of x is equal to x plus the absolute value of x. And we want to, first we want to just write it as a piecewise function. And then we want to check where it's continuous. Okay? So I know it's limits, but continuity and limits go hand in hand. All right, so let's write it as a piecewise function, and feel free to type anything in the chat if you have ideas or want to share how you would do this question. But there's a little bit of a delay, so I'll just explain how I would go about doing it. Let's start with the absolute value of x. Right? What's the graph of the absolute value of x? It looks like this. Right? And so for positive values, it's the line y equals x. For negative, it's y equals negative x. So the absolute value of x could be expressed as, well, it's negative x if x is less than 0. Right? And it's positive x if x is greater than or equal to 0. This equal to sign could be on either, right? Because negative 0 is still 0. But you just put it on one of them. I'll put it here. All right, and now we want to get x plus absolute value of x. Let's just add x to both sides. Or let's add x to every part of this piecewise function. Okay, so x plus absolute value of x would be 0, right? X minus x if x is negative. And then 2x if x is greater than or equal to 0. Okay, so that's how we express it as a piecewise function. And now the question is, where is this continuous? Okay, and it's clearly continuous for x less than 0, and it's continuous for x greater than 0. The question is really going to have, we have to ask is our function continuous at x equals 0? Right? I mean, the function 0 is continuous on its domain, and so is 2x. So when we switch parts is where we have to check. And so we want to do the limit. As x goes to 0, we'll have to evaluate the limit from the left. We'll have to evaluate the limit from the right, and then check to see if those are the same. So let's go to limit. Oops. As x goes to 0 from the left of our function. Well, that's just the limit as x goes to 0 from the left of, okay, the top component, 0, which is equal to 0. Okay, the limit as x goes to 0 from the right of our function, we would use 2x when you plug in 0, you still get 0. And so we can conclude that the limit as x goes to 0 of our function is equal to 0. Okay, that doesn't mean we're continuous. That just means the limit exists, right? I see Razor M got that. So the limit is 0. What's the next thing we have to check? The function, when we evaluate the function at 0, we also get 0. And we do. Let's just check. So f of 0 is equal to, well, x is greater than or equal to 0, so 0. 2 times 0 is 0. Okay, so yes, it is continuous. F is continuous everywhere. Okay, since the limit as x goes to 0 is equal to the function evaluated at 0, it's continuous everywhere. You could check your answer by going to your graphing calculator or Desmos, and you would clearly see you could graph this function without picking up your pencil, right? So what would it look like if we were to try to graph it? On the left-hand side, it's just going to be this horizontal line at 0, and then on the right, it's going to be a line with slope 2. So, I mean, you can see here. Those of you who know a little bit more about derivatives and such, you could ask yourself, is the derivative of this function continuous? And you would see the answer is no. That's a cusp. But for my class, we're not worrying about that yet. We'll get there next week. Okay, so that was question 1. Not too bad. We can move on to question 2, or if anybody has a particular, let me get it out of the way, particular question we want to go over. Just let me know. Again, the questions are in the description. All right, well, question 2, I have a link to a solution video, so I'm not going to worry about question 2. Let's do a more complicated limit. I don't have any questions. The chat seems dead. Yeah, I agree. The chat does seem dead, so we can liven up the chat. But it's just we got a small group here today, so it's tough to have an active chat with a small group. People are probably over watching Black Pen, Red Pen. That's okay. Okay, let's do a more complicated example. I'm going to ask for some help. So this is number 6. So if you're following along with the questions, it's the limit as x goes to 0 of the square root of 1 plus x minus the square root of 1 minus x all over x. Molly says, woo, more complicated limit. Yeah, that's true. Okay. So think about this. I mean, what's the first thing you should do with any limit question? Just try plugging in the value. Okay, so first thing you should do, try to plug in x equals 0 and see what happens. You would get, well, 1 minus 1. Our numerator would be 0 and our denominator would be 0. So if you tried plugging in 0, you're just going to get 0 over 0, which means we got work to do. Okay. And so, yeah, what can we do? Let's take the limit from the left and the right. Yeah, I don't think we're going to need to worry about left hand and right hand limits here. Let's just worry about just going straight up with the limit. So there's a number of things we could do. We can, here we have square root of 1 plus x minus the square root of 1 minus x. Let's multiply by the conjugate. I mean, again, we're going to try things, see what works out. Multiplying by the conjugate is usually a good idea to start. Okay, so let's multiply by the conjugate. What's the conjugate? You just change this to a plus sign. Okay, so square root of 1 plus x plus the square root of 1 minus x. And then the denominator is the same thing, square root of 1 plus x plus the square root of 1 minus x. Okay? And yeah, rationalize numerator, that's a good idea. So yeah, it's another way to say it. Rationalize or a conjugate. And so what happens, our numerator, so this is still, okay, it's important. We haven't evaluated the limit yet, so you should make sure limit as x goes to 0. Our numerator becomes what? The square root of 1 plus x squared squared, which is just 1 plus x, minus the square root of 1 minus x squared. Okay, becomes this. Well, and what's our denominator? Well, it's x times all this mess here. Okay, we won't worry about distributing it. Maybe that's like a worst case scenario. We'll have to distribute. But for now, we'll just leave it like this. All right, maybe you can see where we're going to go from here. We have 1 plus x minus 1 and then plus x. So this is the limit as x goes to 0. So what's the numerator? The 1's cancel. X minus negative x is 2x. Right, so the numerator is 2x. And then what's the denominator? It's x times all that junk. Okay, so this is why we don't want to distribute. Maybe you see it. All right, where can we go from here? So in the chat, I want to know. I saw that my brother is in the chat, and rumor has it he took high school. I mean, he took high school. He took calculus back in high school, so maybe he knows how to do this also. So what can we do? What should we do here? We have 2x over x times square root of 1 plus x plus, yeah, x cancel, right? Yeah, cancel the x, okay? And now, once you cancel, this should go through your mind, we try plugging in again, okay? Anytime you cancel something, you should just try plug in again, see maybe we're done. Okay, now we can plug in x equals 0 and see what happens. 2, our numerator is 2. That's great. We don't have a 0 or an infinity in our numerator, so we know the question is done. It's just a matter of what it's going to go to. So we have a 2 in our numerator, so the question is done. Our denominator is, 1 plus 0, the square root of 1 plus 0, square root of 1. So this is 2, and this is a 1, and this is a 1. And so 2 over 2 equals 1. All right, not bad. So again, what did we do? We saw we had these square roots in the numerator. And so our method, I mean, those of you who know L'Hopital's rule could try L'Hopital's rule. But we don't know that yet. So what we do is multiply by the conjugate and just hope that things work out. And it did. Yeah, so for the purposes of our class, it's going to work out nicely. Okay. So let me see in the chat, I see square root of 1 plus x plus the square root of 1 minus x as x goes to infinity. Yeah, we could try that. Good x goes to infinity question. I think you're going to want a minus. So the way, I can't see, Rayan asked, he wants the limit as x goes to infinity of the square root of 1 plus x plus the square root of 1 minus x. I'm a little bit concerned with this question just because you would be taking the square root of a negative if we try this question. But if we did something like this, maybe a minus and then an x minus 1, we could see that. We could see what this does. So this is not a question from the study guide, but it's similar. So we could look at something like this. Right, and so first thing you should do is just try to plug in infinity and see what happens. And so if you plug in infinity, you got a square root of a big number, so infinity minus infinity. We don't really know what that means. Right, infinity minus infinity, it could be negative infinity, it could be positive infinity, it could be anywhere in between. So if you get, it's called an indeterminate form. If you get like infinity minus infinity, that just means we got some work to do. Okay. Yeah, so we could go from here. If we, again, we have these square roots. So the natural thing we should do, we'll put this over 1 and then multiply by the conjugate. Okay, and so our numerator, again, this is equal to the limit as x goes to infinity. Our numerator the numerator is going to be 1 plus x minus 1. Okay, that's nice. A lot of things will cancel. And our denominator is just going to be the conjugate here. Square root of 1 plus x plus the square root of x minus 1. Okay, and, well, what do we get? The numerator becomes, well, 1. I'll write on the next line because we still have this limit. Okay, x minus x is 0. 1 minus negative 1 is 2. 2 over, all right. And then our denominator is the square root of 1 plus x plus the square root of x minus 1. And I think we're done, right? Oh, it looks like we got black pen, red pen is in the chat. I was watching a little bit of your stream. Nice work today. So now what we can do is plug in a really big number. See what happens when we evaluate at a really large number. Maybe 2, our numerator stays 2, our denominator is infinity, right? And so this will go to 0. Okay, so yeah, again, this was messy. The first thing you should try to do is just plug in the number, plug in infinity, whatever that means. You would get infinity minus infinity, but again, this conjugate method kind of makes things nice. All right, so let's look at another example. All right, so here's an example. This is number 11 in our, if you're following along with the questions. So I'll do it here. So if you take a look at the questions, this one's nice because it's a little bit like a proof we're going to do here. Okay, so if, I guess let me write the question, number 11. Okay, so if 2x is less than or equal to, if 2x is less than or equal to g of x, which is less than or equal to x to the 4th minus x squared plus 2. Okay, so if we have a function, g of x, we don't know what the function is, but we know it's bounded below by 2x, and we know it's bounded above by x to the 4th minus x squared plus 2. The question is, evaluate the limit as x goes to 1 of g of x. Okay, so we know nothing about the function. We have no way to describe the function other than we know it's bounded below by 2x and it's bounded above by x to the fourth minus x squared plus 2. We have to evaluate this limit. Does anybody have any ideas? Does anybody have any ideas of how we could evaluate this limit? We don't even know what the function is. And I know there's a little bit of a lag, so I'll give you, I don't know how long the lag is, 20 seconds. So I'll give you some time to think about this. Think, how the heck can we do this? I see it. Squeeze theorem, yeah, so this inequality should just make you think, oh, squeeze theorem might help us out here. Okay, so the squeeze theorem, what does it say? Is if we have a function that's bounded below by some function and bounded above by another function, well, there's one other thing. It reminds me of the sandwich theorem. Yeah, maybe some people call it the sandwich theorem. I call it the squeeze theorem. So what we need to check is if the limit as x goes to 1 of the bottom function is equal to the limit as x goes to 1 of the top function, then we know anything in between, well, we'll go to that number. So we just have to verify, and this is our only tool, the only tool we have. If these went to different numbers, then we're kind of out of luck. But so let's just evaluate the limit. So this is the solution. The limit as x goes to 1 of 2x. Imagine if I gave that question on the test. Evaluate the limit as x goes to 1 of 2x. Everybody would get 100. You just plug in 1, right? So that's 2. Okay, the limit as x goes to 1 of x to the fourth minus x squared plus 2. Well, again, you just plug in 1. So 1 minus 1 plus 2 is also 2. Okay, so we're allowed to use the squeeze theorem. So the squeeze theorem says if the lower bound goes to some number and the upper bound goes to that same number, then anything in between goes to that number. So by the squeeze theorem, the limit as x goes to 1 of g of x is equal to 2. Okay, so the lower bound went to 2, the upper bound went to 2, so anything in between goes to 2. So even though we didn't know what this function is, we could still evaluate the limit. It's a special case. But where's the Chen Lu? Dr. Payam, welcome to the stream. We don't know derivatives yet in this class. We'll get there though. So yeah, we're still a few weeks away from the legendary Chen Lu. Right now we're just going old school limits. All right. I guess I'll give a little behind the scenes. So I don't know how many of you watch the Minecraft videos I make, but my one coming up is going to be a calculus-inspired video. We're going to do derivatives in Minecraft. It's going to be, could be the first time it's ever happened in human history. So that will be fun. Okay. I guess let's look at another example. So I know we may have done this one in class, but you guys weren't all in class. Wow, sounds really cool. Yeah, I think it's going to be a nice video. The Minecraft is done. The editing has not even begun yet, though. So we'll see how that goes. All right, so let's look at number 12. Yeah, let's squeeze some more functions. Yeah, let's keep doing a couple more squeeze theorems so we can see how this works. So I want you to prove. Okay, prove. I know it's a scary word for a young mathematician. So this is number 12. I want you to prove the following identity. So prove that the limit as x goes to 0 of x to the fourth cosine of 2 over x is equal to 0. All right, so I want you to show or prove. Now, Yeah, I'm not using like an epsilon delta proof, just using more basic techniques. Prove that the limit as x goes to 0 of x to the fourth cosine of 2 over x equals 0. And so one piece of advice is if you're ever asked to do a limit of like sine or cosine of something over x, okay, you got that x in the denominator of like what's inside the cosine or the sine, it's just like begging you to use the squeeze theorem. Okay, so this is just saying, Dr. Wesselgouch, please, for the love of God, use the squeeze theorem. So we'll try using the squeeze theorem here. Okay, so whenever you see this kind of sine or cosine, you should be thinking, we got to use the squeeze theorem. So cosine of 0, isn't that going to be 1? Well, we also have this x to the fourth term. We think goes to 0. But if we tried plugging in x equals 0, what happens? We get 0 to the fourth cosine of 2 over 0. What's cosine of 2 over 0? Right? So we don't know. Maybe is it -1? Is it +1? Is it somewhere in between? Yeah, the answer is nothing. But yeah, we want to use the squeeze theorem. It's between -1 and 1. So let's bound our cosine. So what we're going to do is -1 is less than or equal to cosine of 2 over x, which is less than or equal to 1. Right? Do we believe that? Cosine of anything is, the lowest it could be is -1. The highest it could be is +1. So I know it has a 2 over x here, but that's not a problem. Cosine of anything is bounded between -1 and 1. And then, yeah, what we could do now is multiply each term in this expression by x to the fourth. And we do have to be a little bit careful. If you multiply by a negative number, you have to flip inequalities, but x to the fourth is never negative, so we're good. We can multiply each term, each part of this inequality by x to the fourth, and what's left on the inside will be the function that we really care about. Okay, so let's multiply everything by x to the fourth. So negative x to the fourth. Let's write this correct. Okay, negative x to the fourth is a lower bound of our function we care about, and positive x to the fourth is an upper bound. Okay, and now what we want to do, evaluate the limit as x goes to 0 of the lower bound, evaluate the limit as x goes to 0 of the upper bound, and then the squeeze theorem will say, if these go to the same numbers, then anything in between will go to that number. So let's evaluate these limits. So the limit as x goes to 0 of negative x to the fourth. Okay, again, that's easy, you just plug it in. And that's also equal to the limit as x goes to 0 of x to the fourth. So the lower bound goes to 0, the upper bound goes to 0, anything in between must go to 0. Okay, so by the squeeze theorem, the limit of the inside function goes to 0. Pretty neat. Yeah, so what happens if we have x to the third instead of x to the fourth? Yeah, then you'd have to just be careful and evaluate limits from both sides, but it would work out the same. Yeah, so you'd have to just come in from the right, and then if you came in from the left, you have to kind of flip all the inequalities. So it would just be messier if you have an x to the third instead of an x to the fourth, but it's going to end up, you'll get zeros. So yeah, you have to come in from the right, show that it's 0. Come in from the left. Yeah, when you come in from the left, you have all these signs flipped. Yeah, so squeeze theorem is super useful. And yeah, so how do we know to use it when you get this like cosine or sine of 2 over x, pi over x, 100 over x? Just like, come on, use the squeeze theorem. So have you all seen the squeeze theorem in your classes before? Or sandwich theorem, or whatever you would call it? Yeah, you see it, you probably don't use it a ton, but it's useful. It comes up again. I remember when I taught Calc 3, I like to give a question that involved the squeeze theorem, just to kind of let everybody remember that it exists. Okay. Okay, yeah, this is a good question. So this is, let's look at number 17 and see if we can do this. Okay, 17 is we're going to prove without graphing. Okay, prove without graphing. The graph of the following functions has the following function has at least 2 x-intercepts on a specific interval. Okay, so this is number 17. So show that f. Oops. Okay, show that f has at least 2 roots on the interval 0 to 2. Okay, and what's our function? F of x is equal to x to the x squared minus 3 plus 1 over x. All right, so I said no graphing. Well, you could graph to kind of get some inspiration, but that's not going to be how we answer the question. How do we show that a function has, well, here I said at least 2 roots. How are we going to show it has at least 2 roots on this interval? Any ideas? And if you're not sure, maybe give me a question mark or something in the chat, just so I can see who's following along. We have to find the roots. Yeah, I mean, I guess one way we could do it is just try to do some algebra and see if we could find the roots. IVT, Allie, good answer. I see you're studying for the test tomorrow. Yeah, let's use the IVT. Whenever you have a question that said, especially in a calc class, show that this function has at most blank roots, at most 1 or at most 2 roots, we want to use the intermediate value theorem. And so what did the intermediate value theorem says? If you have a continuous function, which, I mean, I know we're potentially dividing by 0, but our interval doesn't contain 0. So we have a continuous function. So if you have a continuous function and your graph goes from negative to positive or positive to negative, you must have crossed the x-axis at some point, right? That's kind of the main application, at least in calculus, for the intermediate value theorem. Is if you have a continuous function and you go from negative to positive or vice versa, well, at some point you cross the x-axis. Okay, so we're going to use the intermediate value theorem. And so in order to use the intermediate value theorem, well, you need your function to be continuous. So you should first say, well, we have a continuous function. F is continuous on the interval we care about. Okay, so F is continuous on this interval 0 to 2. I mean, maybe you want to give a little more justification because rational functions are continuous on their domain. It's like if you're writing a nice typed answer. A test, this is fine, I would say, especially since it's a times test. So F is continuous, right? It's clearly continuous since the only issue we have to worry about is dividing by 0, but 0 is not in our interval. And so what we want to do is find x values that make our function go from negative to positive and then back down to negative, or maybe vice versa. So we want to check, does our function do this or this. If we could find values that make our function go from negative to positive and then back to negative, or vice versa, well then that means our function crossed the x-axis at least 2 times. All right, that's the idea here. Okay, and so a good place to start is the endpoints. Now the endpoints aren't actually in our interval, so we'll just pick values that are really close to the endpoints. So what happens if we evaluate our function at, let's say, not 0, but maybe 0.01? Okay, you would plug in 0.01 and ask, is this a positive number or a negative number? Yeah, so it jumps over and under 0. Yeah, that's the main idea we're trying to go. We want to go minus, plus, minus. That means it would cross 0 twice, and vice versa, or positive, negative, positive. So if we plugged in a number like 0.01, we're going to need a calculator, but what would you get? You would get, well, that's a small number, negative, and then a massive positive number. It's a positive number. Okay, so you type it into a calculator. If you plugged in 0.01, you should get a positive. And so our function at 0.01 is somewhere up here. Now we want to find a point where it goes negative. Well, let's check the other endpoint. We're close to it. F of, let's say, 1.99. And again, you can type it into a calculator. It's going to be positive. Yeah, our function does go up to positive infinity as x goes to 0, but for now we're not worrying about what happens as x goes to 0. We want to find roots. So we want to find when it crosses the x, we want to find or show that there exists at least 2 times when it crosses the x-axis. Okay, so we know it's positive if we plugged in a number close to 0. We also know it's positive when we plug in a number that's close to 2. So we just need to find a value between 0 or between 0.01 and 1.99 where it's negative. Okay, and a good place to start is just the center of the interval. So let's just try x equals 1. That's usually a good way to start, especially on a timed test. Your professor is not going to be mean and like have you guess 100 different places. So we try x equals 1. F of 1 would be 1 minus 3 plus 1. That's a negative. Okay, and so our function goes from plus to minus back to plus. So it must have crossed. The x-axis at least twice. So since f is continuous, it goes from positive, I'll just write plus, to negative, to positive. It must have crossed the x-axis at least twice. The graph. Okay, so we didn't find where the roots are. We know one of them, I mean, we could be even more specific. We know one of them is going to be between 0.01 and 1, and the other one is going to be between 1 and 1.99. But yeah, the question didn't ask us to find the value. We just needed to show that it has at least 2 roots. What if we plugged in the largest value from our interval? Yeah, so if we plugged in, well, 2 technically is not in our interval, so that's why I used 1.99. But when I used 1.99, we saw they were positive at both endpoints, and so we had to find a negative in between. Yeah, so I used a small a number on the left of our interval, a number on the right of our interval. We saw they were both positive, and then somewhere in between. we found it was negative. Cool question, don't you think? It feels like a little bit more of a proof than a classic calculus question, but I like those types of questions. All right, we can keep moving along. Let's keep going. Let's do another example with the intermediate value theorem. So this is number 18. And some of the, if you're looking at the PDF, some of the questions have YouTube video solutions already. So if you you want to see how I solved it last year, you can click those YouTube videos. Let's just say they didn't get many views back then. It's still growing. The channel is still growing. All right, so we want to find an interval. So find an interval where the equation x to the fifth plus 2x equals x squared minus 3 has a solution. All right, so you could imagine the graph of y equals x to the fifth plus 2x. It intersects the parabola x squared minus 3 at some point. At least I claim it does. And we want to find an interval where they intersect. Okay, and so I kind of gave it away. What we're going to do is we're going to use the intermediate value theorem and use the same procedure. But it's easiest if we bring everything to the left-hand side and have a set equal to 0. Okay, so let's bring everything to one side, and now, so let's subtract it over. Our function will be f of x equals x to the fifth minus x squared plus 2x minus 3, and we want to show this has at least one root. All right, that's what the has a solution is the same thing as this equation having a root. All right, so we want to show that this equals 0 at some point. We weren't given an interval. Okay, so this is a little bit different than the last example where it's just like, oh, try the endpoints and then try somewhere in between. Not much thinking. We don't have an interval here. So a good method is, well, let's just start at 0, plug in 0, see if we get a positive or a negative, and then we're going to have to kind of make an educated guess if we should go to the right or if we should go to the left. See, -2 seems like a negative y value, and 2 seems like a positive. Yeah, so that's a good point. There's going to be a number of ways we could do this, but I like to start with 0 because it kind of just gets us started. So if we try 0, if you plug in 0, you get 0 minus 0 plus 0 minus 3. It's a negative. Okay, and now, again, find an interval. It doesn't say it has to be a small interval. We want to check how can we make this function x to the fifth minus x squared plus 2x minus 3. How can we make it positive? Yeah, sorry. Okay, it should be a plus 3, and so this is going to be greater than 0. Good catch, Mohammed. Thank you. Yeah, so this should be a plus 3. Doesn't really make a difference. Well, it does, but so we want to make this whole expression now. We want to make it negative. How can we do that? Well, x to the fifth kind of dominates, right? If you plug in big numbers, x to the fifth is going to make it is really going to be what controls how this function behaves. So if we plug in a really big negative number, let's say like -10, for instance, you could go overboard and go negative 1,000. But if you try f of -10, well, you would get negative 10 to the fifth. which is negative 100,000, minus 100, minus 20, and then plus 3. Okay, so what's the point? We don't really care if what the value is, we just care if it's positive or negative. It's definitely a negative. Okay, and so our function, this, is continuous, right? F is continuous. And goes from negative to positive on this interval negative 10 to 0. So by the intermediate value theorem, it must have crossed the x-axis at some point. Okay, and so since f has a root, setting our function equal to 0 is equivalent to solving this equation. So these are equivalent equations here. So if this has a root, then this equation up here, has a solution. Okay. What if we plugged in -1? Yeah, -1 might work as well. So that'd be -1, -2, -4, plus 3. Yeah, -1 would also work. So you could be way more precise, right? I gave you kind of a pretty large interval for where the I gave a pretty large interval for where the root exists, but you can be more precise. Could one use the fundamental theorem of algebra just to show that a real root must exist? I'd have to think about that, but I'm sure you could. Yeah. So, right, what's the fundamental theorem of algebra? Says that complex roots come in pairs. So yeah, so there should be at least one real root because we have an odd power polynomial. But yeah, that doesn't give us an interval, so that'd be too powerful of a tool to answer this question. It doesn't quite answer it. All right, so let's do a few more. Does anybody have any particular ones they want to go over? If you want to look at the PDF. Especially those of you who are actually in my class and have a test tomorrow. I know, and I'll let you type in a logarithm. Number 13. Yeah, let's do number 13. Oh, okay. Yeah, so this is a fun question. It's a one-liner, but it's tricky. So here we have, so this is number 13. It says, if the limit as x goes to 1 of f of x minus 5 over x minus 1 equals 2. Okay, so if this is true, what I want you to do is find the limit as x goes to 1 of f of x. Again, I like these questions where I don't really give you what the function is. You got to just kind of think of just in general how it will work. Okay. So let's take a look at this. The limit as x goes to 1, and feel free if anybody has any ideas, share them in the chat. I feel like I've been pretty good reading the chat, so I'll keep reading it. Yeah, so we want to evaluate, so we have the limit as x goes to 1 of f of x minus 5 over x minus 1 equals 2. Okay, so what do we got going on here? So, okay, first thing we should do with a limit, right? What's the first thing you should do? Just, no matter what, try plugging in the number, okay? If you plugged in x equals 1, what do you get? you get, well, the limit as x goes to 1 of f of x up here, minus 5. The denominator would be 0, okay? So we get a 0 in the denominator, and it's equal to 2. Okay? So the limit as x goes to 1 of this expression is equal to 2. What's the importance of 2? Nothing really special. I see Bernard may have got this one. Nothing really special about the number 2, except for does not exist. It's not infinity. It's not negative infinity. So it's a number, okay? So this limit is equal to a number. So the only way that could happen is if you have, well, we already have a 0 in the denominator, so we must have a 0 in the numerator. Okay? So since we have a 0 in the denominator and this limit is equal to a number, you know, it's not equal to infinity or negative infinity, it's just equal to a number 2, we know that this the numerator has to go to 0 as well. So the limit as x goes to 1 of f of x minus 5 has to also equal 0. Right? Why is that? Because the denominator goes to 0. So the numerator also has to go to 0. That's the only way, if the denominator goes to 0, that's the only way you can end up with a number, like 2. Right? Otherwise, you get infinity or negative infinity or does not exist. Right? If this did not go to 0, let's say it went to like 6. But then you have 6 over 0, which goes off to infinity. Or negative infinity, depending on what direction you go from. Okay, so this has to equal 0. Add over the 5. All right, add 5 to both sides, and then we get our answer. Okay, so again, we don't know what the function is. We don't know what it looks like, but we know if you start by trying to evaluate the limit, you get a number, but you had a 0 in the denominator. You definitely had a 0 in the numerator. Okay, pretty cool. I thought that was a nice question. So let's do an example. It's not from the questions that I have listed out, but it's similar. So those of you in the class, you know, we've spent some time talking about slant asymptotes. Those of you who are not in my class, what a slant asymptote is, it's a concept that comes up when you're graphing functions. It's not like a horizontal asymptote, it's when your curve kind of goes off in a line at the end. And so we're working with slant asymptotes a little bit this unit. So let's do an example where we find the slant asymptote. Okay, so find the slant asymptote. But now I'll just make something up, the function f of x. Okay, so when can slant asymptotes exist? Yeah, diagonal asymptotes probably is a name here as well. They exist when the degree of the numerator, if you have a rational function, if the degree of the numerator is exactly 1 more than the degree of the denominator. So let's say we had like x to the 4th. Actually, let's make it a little bit tricky. 2x to the 4th plus 3x to the 3rd, or I guess, yeah, to the 3rd plus 1. And let's have over here x to the 3rd minus 1. Okay, and so we want to find a slant asymptote. Basically, what is a slant or a diagonal asymptote? What is a slant asymptote? It's telling us how our function behaves as x goes off to infinity. It's just not going to be a horizontal line. It's going to go off in a line y equals mx plus b. And so one way to do it is, yeah, so you could solve this this limit that was typed in the chat. Another way you could do this is you could just do polynomial long division. Okay, so this question really boils down to, you could take this question and, sorry, is this an x to the 3rd or an x squared? That's an x to the 3rd here, and that's also an x to the 3rd here. Yeah. So this question can be restated as do polynomial long division and don't worry about the remainder. yeah, x to the third in the denominator. And let's see what we get. So this question you could have done back in high school when we were learning about polynomial long division, but now it's just asked in a different way. So what do? We have x to the third minus 1 on the outside, and then we have x to the third minus 1, and then we have 2x to the fourth plus 3x to the third plus 1 on the inside. And if you like these types of questions, you should take an algebraic geometry class because you got to do this sort of stuff all the time. But okay, how do we do this? You ask yourself, how many times is the leading term of x to the third minus 1? So how many times does x to the third go into 2x to the fourth? And so it's 2x. Right, so how many times does x to the third minus 1 go into 2x to the fourth? 2x many times, right? You multiply them together, you can see that. So then you multiply this 2x to each of the terms, so 2x to the fourth. Let's write this plus 1 over here. Minus 2x. And now you want to subtract the terms. Okay, so you subtract down. This will go to 0. If it doesn't go to 0, you did something wrong. The first term should always cancel. That's kind of how we did it by construction. And now we're left with 3x to the third. 0 minus 2x is plus 2x, and then plus 1. And now you repeat the process. How many times does x to the third? How many times does x to the third go into 3x to the third? That's 3 times. And well, you can't have any lesser terms than a constant term, so we're done. But let's just write it out to confirm. 3x to the third minus 3. And so what we left with is 2x plus 4. All right, and so this line, 2x plus 3, would be what our function looks like as it goes off to infinity. So as x gets really, really large, our function would tend to this function here. Okay, and yeah, so once we get into curve sketching, which is one of my favorite topics. I don't know if you know this, but I once tried to make a viral calculus video. It was called 7 Facts Needed to Graph a Function by Hand. And slant asymptotes, that was one of the facts. Number 2, maybe even number 3. So, yeah. All right, on that note, I think that's a good place. Did I make a mistake? No, I think I like this answer. Yeah, I think I'm happy with it. Yeah, so this was a minus 2x, but when you subtract it, it becomes plus 2x. I think that's a good place to end. So those of you who are in my class, good luck tomorrow. You'll do fine. Get a good night's sleep. And yeah, ask me any questions on Zoom if you have questions. Those of you who are not in my class, thanks for coming. I hope you learned something today, or at least got reminded of some of the calc stuff that you had back in the day. Plug a video tomorrow. I'm publishing a video on a pretty cool series. So if you like series questions, check that out tomorrow. And then I'll have a Minecraft video coming out on Sunday. All right. Well, thanks for stopping by. I'll see you later. All right. Bye-bye.